So today I want to say something about lower bounds and particular limitations of what you can do with a quantum computer. And it kind of fits neatly with the previous talk in some sense, at least the introduction. So in general we are interested in the complexity of a problem, being the number of steps that you need to take to solve the particular problem. For example, as in the last talk, a formula, and we're trying to find the satisfying assignment to that formula, and how fast can we do that. And as we all know, there's two things to do. One is to construct an algorithm, and on the other hand, show that that algorithm is the best algorithm there is. So there's no algorithm that's better. And ideally you have that the upper and the lower bound coincide, in which case you know exactly the complexity of your problem. And as we've seen in the last talk, for arbitrary satisfiability, we really do not have a better algorithm than 2 to the n. I mean, the improvements were only for formulas where there was a 3 set, or the number of variables in each clause was bounded. And on the other hand, the best lower bound we have is n, maybe constant times n.
There are some bounds for general, it's maybe 4, but they are in the form 2 to the m minus something smaller.
Really?
Yes, but this is something non-linear.
Okay, I didn't know that. Anyhow, my ends here are always a little bit fuzzy, so up to non-linear terms. I see I'm
like that?
to hear that. Yes, yes. My tools are very precise now. Can you do that? Okay, so this is the P for this NP problem. Should be in China, you know. So one way out is to define a simpler model, as I did already yesterday, the black box model. What are you looking for, Sasha? Okay, so it's the black box model. It's a simpler model as discussed yesterday, where we have an input consisting out of n variables, and we are interested in computing some Boolean function of these n variables, and we only count the number of variables that we access. For example, the OR function is 1 if and only if not all the variables are 0, or equivalently if there exists a j such that the jth variable is 1. So why am I going to talk about the black box model? Well, first of all, in relationship with quantum algorithms, most quantum algorithms that I know are actually developed in this black box model, except for Shor's algorithm, of course, which talks about factoring numbers. However, if you really look carefully at Shor's algorithm and you look at the quantum part, then that actually does solve a black box problem, and you can formulate that precisely. And thirdly, the classical model is very well understood. We can indeed prove tight upper and lower bounds for most problems that we care about. So it's sort of a good playground to work in and to try to develop techniques that then hopefully at some point will generalize to the real world.
You mean this classical black box? What has been classically?
Sorry?
What has been classically well understood? You mean classical black box model?
Yeah. Yeah. For example, what I mean here is, for classical algorithms, you can, for deterministic ones, you can show that you need exactly n queries. You need to query all of the variables in order to know where the OR is true, and the upper and the lower bound is the same. I mean, that's tight. On the other hand, for randomized decision trees, for randomized algorithms, we know that you still need to query a linear number of variables, but not all. You can sample from them. And also this is tight. You actually cannot do better than a linear amount. And the omega here, the constant there, will depend on the error probability that you allow. And a way to show that is something called the Yao principle, which, if you haven't heard of that, it doesn't really matter. But there's techniques for proving these lower bounds. For the, however, for the, and also in the quantum case, as a matter of fact, and we will see some of that more, the upper and the lower bounds are known, and the complexity is square root of n. For this problem, where the algorithm is due to log Grover, I talked about that yesterday a little bit. And the lower bound is by Bernstein, Brassard, Bennett, and Bazarani. Where it's interesting to note here that the lower bound came before the upper bound. So they first proved the square root of n lower bound, and then later Grover came up with this upper bound. Usually it's the other way around. Okay, so let's zoom in on the topic that I've been talking about 2 days, and that I will continue today. It's quantum black box complexity. And as before, in a general way, so I want to prove lower bounds about quantum algorithms. So I have to tell you the general framework of a quantum algorithm. And a quantum algorithm is something that starts with zeros. Here they are. And you apply a sequence of unitaries. Of course, you may think of this as one unitary, but it will be useful to think of them as t-steps. And then you have your output wires, and you measure, for example, this particular output wire, and that is then the answer to your problem, hopefully, if the algorithm was correct, but that's the answer that the algorithm gives to you.
But where is the input?
It'll come. This is like decision trees. So the inputs will be at the next slide.
Mm-hmm.
But if you don't have decision trees, then the input is all zeros in this case. Mm-hmm. And we have to guarantee that these unitaries are simple ones, like one of these four gates. But this will be talk about relativized complexity. Mm-hmm. That's a term I might also give to black box complexity. Yeah, so in unrelativized version, the inputs are here, in this case, a simple input. And the oracle will come on the next slide. So the probability, note that the probability to output a 1, so the probability of measuring a 1 here, is either larger than 2/3 or smaller than 1/3. And that's the error that I allow. So how does that come about? Let's compute. So this final state that I have here is something, and it can be written as decompose it in my basis state. So it's an arbitrary sum. Suppose that I have k qubits here of all 2 to the k basis states with some amplitude in front of it. And what I'm interested in is the probability of measuring a 1 here, which is equivalent to looking at all the basis states that have at the last position a 1, because they will correspond to measuring a 1 at this position. Take the amplitudes, square them, and sum it up. That's exactly the probability of observing a 1, and we will have that this particular sum either is more than 2/3 or it's less than 1/3, in case we have a bounded error algorithm. Any questions about this? Is that clear? Now, also, I would like to make the distinction of having an exact algorithm or deterministic algorithm, which will have the property that if you look at the probability of measuring a 1 here, that's either 1 or 0. And as we've seen, for example, the Deutsch-Jose algorithm, that's an algorithm that, if you satisfy the promise, will be exact. provided, of course, that all the hardware is perfect. But I'm assuming that everything, all these unitaries are done in full detail and there's no error there. Okay, so now the oracle comes in, Sasha. This is this black box, these T queries. So now the algorithm consists out of a unitary making a query, doing another unitary, making a second query, etc. up to the Tth query, doing a final unitary, and measuring the output. Okay, that's a T query quantum algorithm. Whereas we've seen yesterday, and bear with me for a few slides, I'm kind of defining it here a little bit more differently. I probably should have yesterday to take away some of the confusion. So this query really is something where you put in the variable that you're interested in this case x, or superposition of the variables, and it will give you in this register, it will put the answer of a variable xi. Put in different words, if I put in here a basis state I, b, where b is a bit, then after the oracle query I get I, b plus the answer, plus the value of xi. Yesterday we had that I got -1 to the xi in front. Actually, this is a more natural way of looking at things. And in the next slide I will actually show to you that these two are completely equivalent. So this is also classical, right? If I want to know the value of variable I, and I get the answer in the second register. However, since everything here has to be reversible, I have to specify, I have to sort of not erase the value b, so I just XOR it with the value of xi. Just that if I know the value of xi again, then I can recover what b was. Okay, but just think of b being 0 in this case. Okay? And as before, we can make arbitrary superpositions, and then by linearity, you will get the answer in for all the basis states in the second register. We've seen in the algorithms so far. Okay, so let's now prove actually that this is equivalent to the model I have been talking about yesterday. So this is what this should be b here. What I just defined, and this is what I talked about yesterday, right? You had this -1 to the xi in front of state I. And these things are the same if I, this is another mistake, this should be b also. So if I set this b register into this state, into this tricky superposition. So think of the initial thing b not being 0 or 1, but set it into 0 -1. Okay? And then do the query. So do the query, and then I claim that I get -1 to the xi in front of my state. And this thing remains 1 over square root of 2, 0, -1. Why is that? Assume that my query xi was 0. Then for sure this thing by linearity will be 0 plus xi minus 1 plus xi, which didn't change anything because xi is 0, so it's still 0 minus 1, and -1 to the 0 is 1, so also there's no negative phase. So in case xi is 0, then indeed this corresponds to this. Now, yeah, okay, there it is. And now if xi is 1 and I do the query, note that then flips the 0 into a 1 and the 1 into a 0, which will give me, I guess, 1 minus 0, but that's equivalent of taking that -1 outside and putting back 0 minus 1 again. So in that case, I will get -1 to the 1 in front of it, so the 1 and the 0 have been switched, but multiplying by -1 and taking that outside gives me 0 minus 1 back again. Okay? So these two models are equivalent. If I have if I study the black box model in this query model, then I can easily transform algorithms that expect this into algorithms that expect that, with no
Does it
extra.
really show improvements or only one-way reduction?
Only one-way reduction. Yeah.